Now, we have discussed so far the dual behavior of electromagnetic radiation that led to the development of Bohr model. So, Bohr model, we have to come up with one more topic before that is the atomic spectrum. To understand atomic spectra, first we shall see what is visible spectrum. And to know visible spectrum, we have to understand the term spectrum. So, in this module, we will discuss the atomic spectra of hydrogen, the two types of spectra, absorption and emission spectrum. Now, before we begin that atomic spectra, we should know what is a visible spectra. When a white light is passed through prism, it gets dispersed into 7 colors, Vibgyor. So, this Vibgyor is a continuous series of light of different wavelength. The one which is having low wavelength is dispersed more, that is a violet light, and red light having higher wavelength is dispersed to less extent. And this is how the arrangement takes place. Violet has 400 nanometer as its wavelength and red light as 700 nanometer. So the dispersion, and one of the example of this dispersion of light to give spectra is rainbow, in which all the colors merge into one another and you get 7 different sets of colors without any gap. And this arrangement is called spectra. Now it starts from low wavelength to high wavelength, and the overlapping take place. There is no gap in between, so it's called continuous spectrum. And this visible range lies in between ultraviolet and IR range, which is the kind of electromagnetic radiations. Now when electromagnetic radiation is passed through the matter, which is composed of atoms or molecules, these atom or molecule absorb energy from ground state and they move to higher energy state, that is called the first excited state, or they may move even higher by absorbing energy. Now they will come back by releasing that excess of energy of that same value to its original state, which is called de-excitation of electrons. Now if energy is emitted in the form of electromagnetic radiation, it may emit energy in form of single step or a multiple step. So when it emits electromagnetic radiation, they will have different kind of wavelength, and this may be developed on a photographic plate, which is called emission spectra. So it emitted 3 lights of 3 different color. Continuous spectra had all colors, but emission spectra is fully discontinuous and it has lines and dark spaces in between them and bright line. So it is called emission spectra or line spectrum, in which background is dark and bright lines pertain to specific wavelength. That is, each atom will emit particular light of fixed frequency or wavelength, and that will have a particular color. Unlike the absorption spectra, in absorption spectra you have continuous light but black gaps in between them. A source of light is passed to sample will absorb light, which light it has absorbed, and when you pass it through a prism and develop the photographic plate, you see dark bands from the continuous spectra. Now it's also discontinuous. So between green there is one black line that you can see, which is the emission spectra's place. So emission and absorption are complementary to each other. Where you had bright line, now you have dark line in absorption spectra. The study of emission or absorption spectra to determine the molecular structure is referred to as. So what we understand over here is that the absorption spectra has a background of colored line, colorful background, and in that few lights are being absorbed. In the places the light is being absorbed by an atom, you get dark black color lines. On the contrary, emission spectra, the background is black, dark, and you get colored lines. And if you see the absorption and emission spectra of an atom specifically, so where you had in emission spectra the bright line, in its absorption spectra you will have dark lines. So this is the basic difference between absorption and emission spectra. And why is an atom absorbing or emitting light? When you give it an energy, only then it will get excited, move to higher energy level, and it may come back to the original state by removing excess energy. And that excess energy removed is in the form of electromagnetic radiation, which gives a particular wavelength or particular frequency. Now, emission spectra is also called as atomic spectrum. Each atom has its own emission spectrum. For nitrogen and neon, there are different emission spectrum. Each atom has its own emission spectrum, just like a fingerprint. The emission spectra of sodium, mercury, lithium. From its emission spectra or atomic spectra, we can detect which atom it is, because all atoms have its own specific emission spectra, and Robert Bunsen was the first to identify different atoms on the basis of the atomic spectra. Elements like rubidium, cesium, helium, indium, gallium, scandium, etc. were understood and analyzed from its mineral by studying its atomic spectra. Helium was present in sun was also understood on the basis of the spectra, atomic spectrum of hydrogen. So now we shall discuss the atomic spectra of hydrogen, which has only one electron. When hydrogen gas is discharged, it emits different kind of light. The electron moves to different energy levels, higher energy levels, by absorbing energy, and when it comes back to its original, it emits different kind of electromagnetic light, which when viewed through the prism and developed a photographic plate, we got a spectra. So hydrogen slit, you are passing prism, then you get a photographic spectra, you get the hydrogen spectrum, and in hydrogen spectrum there are different series of spectral lines. This hydrogen spectra was first explained by Balmer. You can see there are different kind of lines that you get by the de-excitation of one electron. So for one electron there are many lines in the emission spectra, and the colored line, first this hydrogen spectra was first explained by a scientist named Balmer. Balmer was able to see only those lines which belong to visible radiation. I hope the second series Balmer you can see colorful lines. In Lyman all are black, in Passion all are green, bracket blue, fund red, but Balmer has all the light. So these lines in which all the higher electron has jumped to n is equal to 3, 4, 5 higher energy level, but from that higher energy level, when it comes back to the second energy level, that is n is equal to 2, it emits light, and that light, all the emitted light falls in visible range. But in other Lyman series, Paschen series, Bracken series, we do not have such kind of visible radiations emitted. So the first explanation for the hydrogen spectra and the equation proposed by Balmer was first given by a scientist named Balmer. Now, Balmer series is corresponding to different light in which the electron is excited from n is equal to 3, 4, 5. In 1885, John Jacob Balmer gave this visible spectra of radiations that were emitted by hydrogen lying in the visible range, and this you can see in the form of spectra. There are different colorful lines for hydrogen atom when it is coming to the lower energy level, n is equal to 2, and he gave a formula to find the wave number, which is equal to 109677 into 1 upon 2 square minus 1 upon n square centimeter inverse, where 2 square represents the lower energy level where n is equal to 2. In Balmer you can see the lower energy level is 2. All the radiation from higher range comes to lower level 2, and n2, that is n, should be greater than 3 or equal to 3. So higher energy level, red light you can see. After that, in 1888, this equation was further modified by Jonas Rydberg, and he gave a formula. Nu bar is 109677 into 1 upon n1 square minus 1 upon n2 square centimeter inverse, where n1 is the low energy level and n2 is its higher energy level. n1 will have value 1, 2, 3, 4 etc. and n2 will have value n1 plus 1. That is, n1 will have any integer value and n2 will have 1 plus n1 or 2 plus n1, whatever, but not equal to n1. n2 should be higher than n1. And this 109677 centimeter inverse is called Rydberg constant for hydrogen. Similarly, Lyman-Balmer-Paschen bracket series has been proposed. The Lyman series belongs to the lower energy level, that is, electrons are coming from higher energy level to lower energy, least possible energy, n is equal to 1, least ground state. In Balmer, the electrons are emitted from higher energy and the least possible energy is n is equal to 2, the energy level. In Paschen, the lower energy level is n is equal to 3, bracket the lower energy level is n is equal to 4, and in Fund the lower energy level is n is equal to 5. So the lower energy level is called principal energy level. So there are 5 spectral lines obtained for hydrogen atom, and each corresponds to different zones, and these are named on the scientists who discovered these spectral lines. The spectral line for atomic hydrogen, Lyman-Balmer-Paschen bracket and Fund, in which N1 are different for Lyman-Balmer-Paschen bracket Fund and N2 is higher than N1, and the spectral region in which they belong is ultraviolet for Lyman, Balmer comes in visible range, Paschen bracket and Fund belongs to infrared radiation. So this is the spectral lines for hydrogen atom. Now why are they giving different spectral line? Because one electron in a hydrogen atom, when it gets de-excited, it is emitting light in different step, and the light emitted is electromagnetic radiation having dual character, and this was taken into account by Bohr, and hence he could explain the spectra.